All right. This screencast is a result of the fact that we did not have class today because of the weather. So this will not have any accompaniment with me working on the board. So what I'm going to do is I'm going to post the screencast for those of you who want to just cover the screencast, and then I'll schedule another day when anybody who wants to can come and we can discuss the material um, using the board and have an opportunity to do uh, questions and answers and that kind of thing. So, halogenation, we're going to talk about that today, how we can put a halogen atom at the alpha carbon. We've talked about halogenation of alkenes, and we've talked about halogenation of aromatic rings. So we know that we can put a halogen on an aromatic ring. If we use, for example, bromine and iron tribromide, we can add bromine across a carbon-carbon double bond. Well, today we're going to be able to replace a hydrogen at the alpha carbon of a carbonyl, so ketones, esters, aldehydes, etc., with a halogen atom, where halogen is either chlorine, bromine, or iodine. We're going to talk about enolates and how we can actually make carbon-carbon bonds with enolates, and that's going to lead us into the malonic ester synthesis, and I also have the acetoacetic ester synthesis listed here. But really, the acetoacetic ester synthesis is nothing more than a malonic ester synthesis in a lot of respects, except you're starting off with acetoacetic acid, and so it's or acetoacetate, and it's more or less the same kind of process. So we won't spend a whole lot of time on that, at least on the screencast. I spent most of my time with that in the regular lecture on the board, and so for those of you who want to go into that in more depth, we'll need to come to the outside meeting that we'll have to make up for today. So you learned during the last lecture that these alpha hydrogens are actually fairly acidic, and they can be removed under basic conditions to give what are known as enolates. Under acidic conditions, they can also give what are known as enols, which react very similarly to enolates. And so it turns out if you have a carbonyl containing functional group, ketone or aldehyde, for example, here, you can replace one of these hydrogens with a halogen. And X here, again, can be iodine, bromine, or chlorine, not fluorine, of course, but a large variety of the halogens. And you can replace that hydrogen with a halogen atom. And so this is actually a fairly useful reaction because we know that these types of halides can actually be useful as electrophiles or other types of molecules for a variety of purposes. So for example, if you take cyclohexanone, you bubble chlorine through it under acidic conditions. So we're generating an enol here. You can generate alpha chloro or cyclohexanone very, very easily. The yields here are typically quite good. For practical reasons, chemists in the laboratory typically don't do chlorinations because you're dealing with gas, and we typically just do the brominations because liquid bromine is easier to deal with. And so you can take a ketone, bromine, and acetic acid, and in this case, acetic acid acts both as the acid catalyst that promotes the reaction as well as the solvent. So it's pretty convenient. And in fact, you can actually buy bromine and acetic acid directly from chemical suppliers, which makes this reaction even more convenient because you simply just take the two, mix them together, and you get the alpha bromoketone in this particular case. Now, the mechanism for this is fairly straightforward. The acid protonates the ketone. So the ketone oxygen reacts with the acid, and you get a protonated ketone, which of course now has a weak pi bond. And the acetate anion that's generated can function as a base to abstract the alpha hydrogen, and you end up generating an enol, and you get your acetic acid back. So it's catalyzed in the acetic acid, so you never consume it, which is why it also can function as a good solvent here. It's not actually being consumed. We know that these enols are actually fairly nucleophilic. This carbon actually behaves as a fairly decent nucleophile, and that's because the oxygen of the enol, those electrons can come back down to form the pi bond of the carbonyl, and the carbon-carbon double bond now can reach out as a nucleophile, if you will, and react with the bromine. And so that generates a carbon-bromine bond at the alpha carbon. We now have bromide, which comes in and deprotonates, of course, the ketone, and you end up with the bromoacetone in this case plus hydrogen bromide. So this is the mechanism overall for the alpha bromination of a ketone. In this particular example, you can see that this molecule has two alpha carbons that are identical. Doing acid catalyzed bromination, you end up generating a bromine at the alpha carbon. And now when we heat this up in the presence of bromine, we can actually, in the presence of pyridine, the pyridine can act as a base and abstract a hydrogen from the beta carbon. That then can form a pi bond, and we've got a good leaving group here. And so we can end up doing a elimination of HX to give alkene. But in this case, it's a special alkene because it's conjugated with the ketone. So this is what we call an alpha-beta unsaturated ketone. And these are useful molecules for a variety of reasons. For example, you might want to use this as a dienophile in a Diels-Alder reaction. And so you can make these from these ketones through this elimination process. So this was an example that you all talked about last week in class when I was gone. So one way in which you can take this molecule and convert it here, right, would be to brominate at this alpha carbon and then do an elimination, and you can get that. The way that we can get to this halogenated compound is we can, of course, we've got the alkene here. We can add bromine across the carbon-carbon double bond and then treat with base, which would take the acidic proton, eliminate this bromine that we would put on, and that leaves that bromine there. And so you end up with this alpha bromo, alpha beta unsaturated ester here. Now, halogenation under basic conditions can be more problematic. So for example, if we look at propiophenone, we have two acidic hydrogens, and if we treat this with bromine under acidic conditions, we'll replace by and large just one of the hydrogens with a bromine. But under basic conditions, we actually over-halogenate. So actually both hydrogens will get replaced with bromine. Now if that's what you want, that's a pretty good deal, so it works out in your favor. But quite frequently you just want to put on one bromine, and so you would not want to use basic conditions. And the question that I ask here is why? And so I want you to pause this for a second and actually work this through step by step. Replace one of the hydrogens in this molecule with a bromine and leave one of the hydrogens on. And ask yourself, why would the second hydrogen be readily replaced? It has to do with acids and bases. I'm not going to give you the answer on the screencast, but work through it and understand why under basic conditions stopping at monohalogenation should be difficult. We can also generate enolates and then alkylate those with alkyl halides to make new carbon-carbon bonds. And you'll recall that I told you that there were only a handful of ways to make carbon-carbon bonds. And this is actually one of the last ones that we'll actually be talking about this semester. Also recall that LDA is lithium diisopropyl amide, which is a strong base. And so you can take a ketone, react it with this strong non-nucleophilic base at very, very cold temperature, and you can generate an enolate. Now remember, an enolate has this resonance structure, and it also has the resonance structure where the oxygen has the negative charge. But the carbon is actually the nucleophilic atom, not the oxygen. And think about it in terms of electronegativity. Carbon's less electronegative, so it's willing to share its electrons more readily. Whereas oxygen, being more electronegative, wants to hold on to its electrons more tightly. So the less electronegative atom usually is the one that functions as the nucleophile. And so we have this SN2 reaction, and we form a new carbon-carbon bond. So let's look at some examples. Again, acetone, LDA, tetrahydrofuran, minus 78 degrees. These have to be run at very cold temperatures. You generate the enolate, then this reacts with an alkyl halide, in this case methyl bromide, and we form a new carbon-carbon bond. Primary alkyl halides work really well for this, but also you'll find that you can use allyl halides. In this particular case, we're using allyl chloride. We've generated the enolate. It will react and we form a new carbon-carbon bond, but also now have incorporated in this new alkene. So now we have a carbonyl over here, we have an alkene over here, and so now we can do all kinds of different types of chemistry. Molecule. We can add things to the alkene, we can add things to the carbonyl, we could reduce the carbonyl, we could reduce the alkene. The number of things that we could do is actually quite large. But the important thing is here we're forming a new carbon-carbon bond. Now, in these two examples, it's pretty straightforward because both alpha carbons are identical, so it doesn't matter which one of these alpha carbons gets deprotonated, you'd end up with the same product. But that's not always the case. And so, if you look at some examples here, we're starting off with a molecule that is achiral. We use LDA to generate the enolate, and then we add a molecule here, ethyl iodide, which goes to the SN2 reaction, and we form a new stereogenic center. So we have one stereocenter. This carbon has four different things. It has a carbonyl, it has this alkyl group, it has this alkyl group, and a hydrogen. But we're going to generate it as a racemic mixture because, again, we have no chirality to start with. So we have to end up getting a racemic mixture of this, an achiral product, even though we have a chiral center. Now here's an example where things get kind of interesting. So if we look at this molecule, we see that we have an alpha carbon that only has hydrogens, and then we have this other alpha carbon that has a methyl group and a single hydrogen. And it turns out that if you react molecules like this with LDA, a very potent base, at very cold temperatures, you always generate the kinetic enolate first. And the kinetic enolate is the one that is the least substituted. So it removes the hydrogen from the least substituted carbon of the two choices that it has. And the reason that it's the kinetic enolate is because LDA is fairly big, and so it goes after the most accessible hydrogen. If it tried to remove the hydrogen here, it would get in the methyl group would get in the way. So we can generate the kinetic enolate, and then we can use another alkylating agent. In this case, they're using iodomethane, and we can put a new carbon-carbon bond, and we end up with 2,6-dimethylcyclohexanone. Okay, so under low temperatures, very strong bases, and polar aprotic solvents, we can generate kinetic enolates. However, what if we want to do chemistry at this carbon through enolate chemistry? Well, fortunately, we can do something about that. So you'll notice here, we can do the chemistry at the most substituted alpha carbon if we change the conditions. Notice what's happening. We're going from a very strong base to a weaker base. This is sodium ethoxide, in ethanol. So we've got a weaker base, a polar protic solvent, and much higher temperature. This is at room temperature or higher. And these conditions are what give us a thermodynamic enolate. Okay, and so this is the thermodynamic enolate because it's on the most substituted carbon. It's the most stable. So if we draw the resonance structure for this where we put the negative charge on oxygen, you'll see that the carbon-carbon double bond here is the most substituted. Now when we take the thermodynamic enolate and react it with iodomethane, we get an SN2 reaction, and we actually make a carbon-carbon bond on the most substituted carbon. So the cool thing about this is that we can place that methyl group regioselectively. That is, we can pick which alpha carbon it goes on by being very careful about how we choose the conditions. So you need to memorize this. Things like LDA, THF, and really cold temperatures favor the kinetic enolate. So you need a strong non-nucleophilic base, a polar aprotic solvent, and really cold temperatures. That will give you the kinetic enolate. If you use weaker bases, polar protic solvents, like ethanol in this case, and higher temperatures, like room temperature or higher, you favor the thermodynamic enolate. And so we can choose how the carbon-carbon bond is being formed by carefully choosing our reaction conditions. It turns out that these types of enolate reactions are actually quite important. So if you look at the preparation of tamoxifen, many of you may know what tamoxifen is. It's a potent anti-cancer drug, and it's used an awful lot in the treatment of, in the treatment of breast cancer. It's a very simple molecule. It's got 3 aromatic rings. It's got an alkene, it's got an ether, and it's got a tertiary amine on it. And this is actually made using nothing more than general chemistry and sophomore level organic chemistry reactions. So starting with this ketone, sodium hydride is a strong base. It removes one of the ketone alpha hydrogens, generates an enolate. They then take this enolate, react it with iodoethane, which makes the new carbon-carbon bond that you need here. And then through several steps, they make this. And so at this point, you don't know what all these several steps are, because I'm not going to go through them today, but you can actually go from here to here on your own. And I want you to sit down with a piece of paper and go from B all the way to tamoxifen. You can do it. You have all the chemistry that you need to make that happen. So I want you to work on that, and then on Wednesday in class, we're going to start, before we get into the day's lecture, by looking at how we could take intermediate B and get all the way to tamoxifen. So bring your notes with you on the your proposed synthesis of going from B to tamoxifen. The last thing that I'm going to talk about in the screencast is the malonic ester synthesis. The malonic ester synthesis uses malonates, which are, this is an example of diethyl malonate. We've talked about these before when we've talked about pKa values, so you might want to go back and look at see what the pKa value is for these alpha hydrogens on a malonic ester. And it turns out that we can remove one of these hydrogens, right, because they're acidic, and we can generate an enolate of a malonate and then make a new carbon-carbon bond. And then through some other chemistry that I'll talk about on Wednesday, we can decarboxylate one of these esters and end up with a new carboxylic acid. So the malonic ester synthesis is a new way to make carboxylic acids. So it needs to be put in your toolbox for making carboxylic acids. You also need to focus on the acetoacetic ester synthesis, which is in the chapter, okay, which deals with making ketones instead of carboxylic acids. But we'll talk about that some more as well. So again, what happens is we put an alkyl group on a malonate, and then you can hydrolyze the esters under acidic conditions to these beta-malonic acids, or so-called beta-diacids. And we talked about that when we talked about the saponification of esters. So we know we can saponify esters under basic conditions and get carboxylates. We can saponify esters under acidic conditions and get carboxylic acids. But these beta-diacids actually undergo an interesting reaction. They actually decarboxylate, and they lose one molecule of carbon dioxide. And it goes through a reaction mechanism where you have 6 electrons moving. And so if you think about this, we've got this OH that's in the present or in close proximity to this carbonyl. And so you push the electrons like this, you lose carbon dioxide. You end up with an enol of a carboxylic acid. And we know that enols are not stable. They tautomerize to the carbonyl form. And in this case, that carbonyl form would be a carboxylic acid. And we'll talk more about that later. So had we met today for class, we would have been working problems on the board dealing with the malonic ester synthesis and the acetoacetic ester synthesis, but we didn't have class today. So watch this pencast. When we come into class on Wednesday, I'll spend maybe 10-15 minutes talking about some of the malonic ester and acetoacetic ester syntheses and answer any questions that you may have.